Later this semester, we're going to do an experiment involving a simple pendulum. It's going to involve one of these bowling ball pendulums like I have right here. And the thing we're going to be interested in is measuring its period of swing. And in particular, we're going to be looking at, like, well, does it make a difference if it's swinging with a very small amplitude versus a very large amplitude like that? So maybe something to look forward there for the later part of the semester to look at that. I've written up here some, actually for the moment I just made this data up, but let's say that I got this period for the small amplitude swing, this period for the large amplitude swing, and then in ways that I'll share with you again later this semester, I determined errors for each of them, and for some reason one's a little bit larger than the other in this case. The thing that I'm asking though is, are they the same or are they different? And the answer for how to do that is what we're going to refer to as the simple discrepancy test. Now, there are a lot of kinds of tests out there. Like, you have some data and then you ask a question. There are lots of tests. In fact, there's a whole class out there known as elementary statistics that focuses on studying that type of question. Here's some data, what kind of questions can we ask and how do we answer them? And it turns out this simple discrepancy test is so simple you won't find it in a single statistics text. But it's simple enough for physicists like me, I'm going to say, and for our class it's a really simple thing to do. So that's the reason why we're going to often do it. It's not the only way that we're going to have of testing some data and asking, like, what does it say? But usually the way the test runs is we ask a simple question that has kind of a binary choice of answers. Like in this case, it's like, do these two numbers agree, yes or no? And we have to take into account what the measurement, what the estimated errors for the measurement say about that. So in this case, one simple way of looking at what the simple discrepancy test does is if you rewrite the original measurements in interval notation. So I'm hoping interval notation is familiar. In other words, a lower bound and an upper bound implied by these plus or minus numbers, right? So if I take 2.53 minus 0.04, if I did my subtraction correct, that is 2.49. I've kept the units in there because this is a physics class and we do that. It's pretty obvious, though, looking at these two numbers and these two numbers, that there's no overlap between these intervals. The lowest number on the higher measurement is above or higher in value than the upper bound for the lower measurement. So that makes it pretty clear there's no overlap. So that would make one be inclined to think that these two do not agree. The way that we're going to do this with a simple discrepancy test, and if you like to do interval notation, if that's how you want to do it, that is fine, but there's another way as well, and that's going to involve doing two things. One is we're going to find the actual discrepancy between these two measurements. This is why it's called the simple discrepancy test, because this is what we're looking at. And discrepancy simply means, well, how different are these two numbers? In other words, 2.61 minus 2.53. When I ask how different are the two numbers, I literally just take the difference. If you look in text, or if you look in the page that's going to accompany this video clip, I will probably write this with absolute value, but really you're just taking the difference. Just put the larger one first if you don't want to get a negative number, right? So in other words, we don't need to overcomplicate absolute value. I think this is 0.08 seconds. Okay, so that's the discrepancy. And then we're going to add up our errors. So I'm just going to write errors here. You could say sum of errors, but I'm just going to add up the two errors that I have. So 0.03, oops, 3 seconds was associated. I'm trying to associate the two, I guess it doesn't really matter. But this is additive. 0.04 seconds added. So basically I'm adding up all of the errors that contributed there and seeing which one of these is larger, the discrepancy or the error. So the errors tells me how much, typically would I expect, maybe you could say on average, but how much would I expect the discrepancy? How big would I expect the discrepancy to be? And then this number is how big the discrepancy actually was. Now, when this number is larger than this number, that tends to say that these two numbers failed to agree. So I'm just going to say failed to agree here. However, there is a little bit of wiggle room here because this is pretty close, right? And we've argued that part of the meaning of errors is that maybe roughly, it turns out there's an empirical rule, it comes from statistics, that says around 68% or so of the time, if everything is behaving the way you think that these numbers are describing it, at least to behave. If you did repeated measurements of the same thing, 68% of the time it should fall within that interval. That still leaves, like almost a third of the time where it should not, right? What if that's just what happened to occur here? So maybe am I being a little bit premature by saying this? So maybe I should say fails to agree at 1 sigma is terminology that I like to use. In other words, just 1 times the reported errors. But what you can also do as an option is do 2. Sigma actually refers to the Greek letter sigma, which is often in physics used to symbolize errors. It actually stands for the population variance in statistics. But anyways, we're going to say 2 sigma error here. And, oops, make sure I spell error correctly before I make a real error or mistake. Anyway, the 2 sigma error would basically say I'm going to take these 2 numbers, but then I'm just going to multiply that by 2. In other words, double what I had here, which would make it at 0.14. And this would say that the numbers, they do agree at 2 sigma. So that's something that we'll be able to report in that way in this class, because it gives us just a little bit more of a comfortable window for agreement, which means that we're reporting our estimated errors, but sometimes it's hard to get agreement exactly within that, just because it's hard to be really as precise as we're saying we're being, and we want to give ourselves just a little bit more wiggle room, accounting for the fact that errors may be like just at 1 sigma are a little bit too restrictive compared to sort of outliers that do actually occur in reality, so we're kind of allowing ourselves that. It turns out, if you ask like, well, is this really what people do? And it's a version of it. There are significance levels that are established for different statistical tests, and what I'm doing here kind of has a rough correspondence to that. So in that sense, there is validity there. It's just maybe for other more advanced kinds of tests, it's reported sometimes a little bit differently, but sometimes also not. These terms of 1 sigma, 2 sigma, physicists will even sometimes say, like, if something is really badly in disagreement, they will say, oh, that was like a 7 sigma disagreement. That means that the discrepancy was larger than 7 times the reported error, right? But in this case, since the discrepancy was smaller than double the total accumulated reported error, that's why we're saying it does agree at 2 sigma.